Welcome to today's master class on reliability. Today we're very fortunate to have Joe Jackson as our guest speaker on this topic. Joe is a nuclear engineer and a staff member at Los Alamos National Lab and has been doing programming and simulation modeling for 31 years, 17 of which have included work with Extend and ExtendSim. During this time, his modeling projects have focused on system capacity, probabilistic risk assessment, and overall system reliability. The types of systems he has modeled include nuclear reactor thermal hydraulics, production of special nuclear materials, nuclear weapon manufacturing, disassembly and disposal, chemical analysis of nuclear materials, and fabrication of nuclear fuels. With that in mind, I think it's safe to say that Joe's reliability concerns probably far outweigh those of the average modeler, and as such make him a particularly good choice to speak on today's topic. Okay, so without any further ado, I guess we can get started. Joe?
Thank you, Anthony, and welcome to everybody. I hope I have a presentation that interests you. As Anthony said, I do a lot of simulation modeling, but not all of it is mainstream. Basically, the focus of this presentation will be the reliability modeling for production processes. The seminar will not deal with product quality or acceptability modeling. Now, even though those features affect product quality and acceptability, I won't discuss them just as a way of keeping the time down. What we really will be talking about is production processes which have many events or interruptions or other occurrences that impede production. Now, events occur at many levels. They can affect the entire facility, they can affect a single room, or they can affect a different single machine. All right? Now, the events, today's presentation comes with several caveats. My modeling techniques have evolved over the 30 years I've been doing it, but the environments I simulate are highly specialized. Some of the concerns we have don't concern everybody else, but you may get some value out of it. So the bottom line is that your mileage may vary with what I'm presenting, and because there are many ways to skin a cat, nothing that I'm presenting is set in stone. In fact, even what I use, I start with as a building block, and from there I customize it almost for every application. So the first thing we need to get down are some terms. The first question we ask is, what are events? For my models, an event is any change in the state of the system. That includes shift changes, resource availability changes, and if a resource is not explicitly modeled, its availability may be simulated using events. Okay? So maintenance operations are a class of events. The classics, the interruptions, the breakdowns, and the failures, and even, it's catching up, even things like environmental conditions. We have operations that we model that depend on being at a critical temperature. They can't happen if the room gets too warm or if the room gets too cold. So we have to model environmental conditions as well. Note, just because we have an event and that event impedes production, it's not necessarily a failure. For instance, shift changes can happen. Nothing failed. They were scheduled. They were planned, but they do impede production. For consistency, we'll refer to the event as the period of time that operations are down. So shift changes are, the event is while the operation is off shift. One of the special notes is that events can happen at times when they will have no effect. For instance, a lightning strike can kill your power, but if it happens at night and you're not running, it will not impede your operations and have no net effect. This kind of emergent behavior is a particular benefit of simulation modeling. People do a lot of reliability assessments using spreadsheets and other tools, but those tools can't really deal with the kind of randomness where an event, how do they account for events that happen when they don't have any effect? Okay? So the types of events we're looking at, as I've said, are shift changes. They can be scheduled, or they can be unscheduled events. And here we've popped up some of the blocks we use. For shift changes, we use the standard shift change block. For scheduled events, we use create blocks. And for unscheduled events, we typically use the shutdown block that you and I have worked on so much. Okay? So some terminology. We have the time between failures, is the time interval between events. All right? Time to repair is the duration of the event. Not necessarily always a repair. It may be just something that has to run its course and then you come out, but we'll refer to it as the TTR. All right? There's time to failure, and that is the operating time, which we'll define later, that must pass before the next event. This comes into play when we start modeling the different ways that events can stack up. So if the time between failure and the TTR are independent of each other, they stack up as you see in the diagram. One time between failure occurs. At the end, when that failure occurs, the repair processes start. But just because you're in a repair mode does not mean that you won't be elapsing time towards your next failure. So in this case, TBF equals TTF. When failures are independent of each other, the time between failures will not start running until the repairs have completed and the object comes back online. All right. In the help text for the shutdown block, the example is given of the bike. And the bicycle, when it has a flat tire, no longer accumulates wear on the tires until the tire has been repaired and the bike is back on the road. In this case, the time between failures equals the sum of the time to repair plus the time between failures, or the time to failure. We're going to assume that everyone has sufficient experience configuring shift and create blocks so that we can discuss some of the intricacies of the shutdown block. Now, of special note, major changes took place in the shutdown block for version 8.02. Its new behavior is significantly different than it was in previous versions of ExtendSim. It's not incompatible. The block will still come up and run, but the results it produces were significantly altered. Okay, with a shutdown block, we have the two modes for determining time between failure intervals. The first option is, does it come up, is progression of time. Items progress towards failure in proportion to the passage of time. We have mechanisms to change how we count that time, but in all cases it's proportional. That option is selected here in the shutdown block by choosing progression of time right here in the dialog box for failures caused by. The other major mode we have for the shutdown block is number of cycles. In this mode, items progress towards failure in proportion to the number of operating cycles. And how you count those cycles has a significant impact. This is the other option in the dialog box for failures caused by. Okay? Now, for controlling how we count operating time, if we connect a value signal to the where connector, then the input at the where connector, if a value is input at the where connector, operating time will be that where signal multiplied by simulation time. In simple cases, failures are true-false events, and operating time would accumulate when where was true. However, this feature of the shutdown block allows us to consider some other options. Okay? Consider the case where the rate of wear and tear of a car's engine is a function of the speed the car is driven. To model this, the input at the where connector would be a function of the speed, some proportion factor. And then the wear value would thus be relative to the multiple of the wear and the base speed. Note that, come on, the wear function is not limited to true, false, and the wear function does not affect the TTR value. So connecting a wear signal does not impact the time it takes to repair once a failure has occurred. Now, the model allows negative wear values to be input, but I have never tested to find out what their effect is or how they operate. The model just doesn't seem to care, so use those at your own risk. Now, another option is we can connect a true-false signal at the schedule connector. The schedule connector is a way of merging down signals. So if the value at the schedule connector is true, the value output of the schedule block will also be true. In essence, it's saying that a shutdown has occurred at a higher level and you are down independent of what this particular shutdown block thinks. Now, the progression of time in TBF and TTR intervals can be stopped or started using this shutdown connector. So you can choose that scheduled downs, they either preserve both TBF and TTR, or they ignore, or they can reset it. Now, the shutdown block can also use a shift. The effect of shift changes is chosen just as the effect of scheduled downs. We can shut down, we can use a shutdown shift and select it in the activity block. And similarly, the TBF and TTR intervals are affected the same way, and we have the same options for controlling them. Now, the other mode for controlling the shutdown block is number of cycles. Items progress towards failure in proportion to the number of operations performed. And here we see how that is selected in the shutdown blocks dialog. Now, if you select number of cycles, a value must be connected to the cycles connector. The block actually flags if nothing is connected. The value at the cycles connector is a monotonically increasing number. We're counting the number of operations, therefore it must always go up. We don't have a thing called a negative operation. Okay? The number of cycles is intended to be connected to the TD output connector of an activity block, but how you connect and determine your cycles determines what you get. Because number of cycles is inherently an integer function, the failure occurs as soon as the number of cycles exceeds the threshold value. And it's always rounded off to the nearest integer. Okay, so it's catching up. So the number of cycles, as soon as it exceeds your threshold or your cycles between failures value, the operation occur. And how you count cycles, therefore, affects the results. What I mean by that is if you connect to a TD connector, the TD connector advances when an item leaves an activity block. So using that signal, your failures will always occur just as items leave the affected activity. If you, for instance, put an info block in front of the activity and count items as they enter, your failures will always occur right when the activity starts processing. Those are both valid models for different situations. There's nothing inherently wrong with either one of them. But the other case where a failure will occur somewhere during the cycle requires some extra code and maybe actually better switch to a different form of counting how your time passes. Okay? Now, one of the problems we have with the shutdown block is that in many cases the scale for the time between events may not be the same as that for repair or recovery processes. For instance, lightning occurs when it occurs and doesn't care what shift your plant is on, but the repair operations may depend on you being on a shift. The shutdown block only gives us one shift and one schedule connector, And so if we have different time scales that we're measuring time between failures and time to repair on, we have to use a different, slightly more cumbersome structure. In addition, your time to repair may be affected by other failures. If the plant is totally shut down, perhaps due to a release of radioactive chemicals, there may not be anybody in the plant to do the repairs until another situation has cleared itself up, namely the cleanup. Sometimes the start of repairs can be forced to wait until all operations in the area have been shut down. If a furnace is operating when it fails, it will be too hot to repair until the furnace has cooled, and repairs will wait. So just to deal with this, we use a structure that I'll show you here. We use items. We create our items to represent our events, either with the create or the shutdown block. And we can actually, due to features in the new shutdown block, use multiple item generators in combination. So we can have events that are generated on a time scale of calendar time. We can have events that are on a time scale with a shift. We can have other events generated that are based on cycles between failure. So while you can use multiple shutdown blocks and merge those signals, we'll in our structure just show one for simplicity. In all these cases, we store the time to repair, the time it will take to recover from this event, as an attribute on the item, and feed the item into an activity block. By enabling the shutdown connector on that activity block, we can put in signals that say, this repair can't happen. For instance, we can put the activity block on a shift, or we can have other failure signals that say, this repair process is itself being interrupted and will take longer than anticipated. Because the shutdown block prevents items from coming into the activity, we need to put a queue in front of it to catch events that have been triggered, but which are not yet in the process of their repair. Once these events are done, we can throw them away. They're strictly there to generate the signals. And because we need to know whether an item is in the queue waiting to start repair or in the activity in the process of repair, we surround the entire setup with a gate block, and we count the number of items in the area. A decision block then looks to see if any items are present and puts out a true-false event signal. For my purposes, I write all of those signals into the database. The many event generators that are represented in a typical model can each have a separate entry in the database, and all of the people, all of the processes, all of the machinery that cares about the status of any particular event can query the database to find out what is the status of the events that affect them, without necessarily being tied to looking at all the events that are in the model. The shutdown block allows for many items to be put in a single table, but that has certain implications. While we can combine the signals from multiple events into a single signal, we have to be careful that we look at what their combination events will be. We can merge the events, we can use logical combinations, but each activity that uses a combined signal must have the same response to all the combined events. If we have two events, event A and event B, and a process downstream responds differently to event A than it does to event B, we will need to split that combination up and put those items in as individual events. The evolution of the model towards greater and greater detail has the tendency, therefore, to break up your event combinations, and everything tends to work its way back to one event generator per event, and the number of combinations that we achieve gradually diminishes over time. Now, looking at ExtendSim, there are 6 possible event responses that have been of use to me. Again, your mileage may vary. The possible events responses are, first of all, I ignore it. That's the last time we'll mention that one, since it's the trivial and obvious case. One event's response is that I do not start processing while this event is happening. That means I can continue processing things that have started already, but I won't start anything new. I can delay an event. Ironically, one step got skipped, which means that events happen which prevents the start of an item. Delays are similar to no start, except for the case that once a delay has been triggered, if it happens when an item is not available or in process, that delay signal will be held and applied to the next item to arrive. We have the no movement condition. This is a case where the systems necessary to move an item away from an activity are down. The no movement case does not prevent processing of the item, but prevents that item from leaving. And if there are limitations on your activities that say you cannot process a second item while the first item is there, then the process will be forced to shut down until the first item can move on. We also have the stop and resume. This is the case where we get interrupted, but once the interruption is terminated, we can resume processing from the point where we left off and no additional time is lost. The opposite of that is the stop and restart. In this case, if an event interrupts me, I must restart from some previous point in the process, not always from the beginning, but I must repeat some actions. Then there is the stop and release, which in Extend terminology is the preempt signal. An event has happened, and the item can no longer be processed on the current machine and must be removed. Once an item has been released or preempted, we can program any response we want, because we will now have that item. So this is where the plus in 6 plus comes in, because if your behavior doesn't fit the 6 that are working there, then you model something special by releasing it and putting it into your own custom code. Now, most of the desired responses can be provided individually by the available options in the activity block. The no start case is selected when we enable shutdown and choose finishing processing items before shutting down in the dialog of the activity block. The stop and resume similarly can be chosen when we say keep items, resume process after shutdown. Stop and restart is keep items, restart process after shutdown. And the stop and release is where we use the preemption option. We enable preemption, put a signal in on the PE connector, and we choose to, in all cases that I will talk about, we choose to preempt all items currently in processing. Now, Extend has interesting options for passing in items with particular values that can preempt individual items in process, but I won't talk about those as a way of just limiting today's scope. Another option is, especially for the preempt tab, we store the time remaining in an attribute value. This is the time remaining in the entire process. When it's preempted, we can reset that to any value we want. We can also examine the time to remaining value to determine what phase the process was in. And we'll talk about phases in a minute. Now, a special note is that a signal on the preemption connector does not prevent new items from entering the block. This is an artifact of the fact that the preemption could have just interrupted a few of the items in a block that has a capacity larger than 1. And because of that logic, putting a preemption signal does not stop new items from coming in. If you want your preemption signal to act as a shutdown, you will need to add some code to tie it to the shutdown connector. Now, the problem with our individual responses is that activities are usually affected by multiple events. There are shifts, there are power failures, you can lose your vacuum system, you can not have your labor. All of those events can affect the same process. But all of those events can happen simultaneously or independently of each other, so they all must be connected to the activity block at the same time. The activity block, it provides only an either-or type logic for selecting how you will respond to the event. Different activities can respond differently to each event. The same event can trigger a different response in one process than another, and the event signals must be connected so as to provide the desired responses, and their connections have to be customized for each application. The response of an event to an event can also change during the phases of the activity. For example, let's consider a baking oven. A failure of the oven while during heat up, when nothing is in it, has a different response than a failure of the oven when everything is starting to rise and the furnace gets turned off. So because we have different responses in different phases on the same equipment processing the same item, I typically divide my activities into phases. The phases are designed and divided according to what activity responses will be available and what resources are required. So in addition to considering what failure modes can happen during that phase, I also consider things like whether labor is required during that phase. Going back to our baking analogy, a man may be necessary and have to be present to load the furnace and to unload it, but he is not required to be there while it bakes. So for both labor representations and resource utilizations, and for our responses to failure modes and events, we divide our processes up into phases. Now, my solution, and again I stress your mileage may vary, is I use a quasi-standardized structure that provides the desired functionality. The 6+ standard event responses and the individual model concepts are presented in detail in what follows. We'll present them individually, and then we'll talk about a combined structure that I use most of the time. So for the no start event, we simply put a no start into a not signal and put that on a gate. The no start, going back to our definition of event, is the downtime, and the gate wants to know when it is open. So we have to negate the no start signal and then feed it to the gate. Note that this allows activities that are currently in process in the activity to continue processing. It only prevents new items from starting. In the no movement case, we have the opposite end. The gate is put after the activity to prevent items from leaving, and again the no movement signal has to be negated to provide a positive signal to the gate. The delay structure is a bit more complicated because of the requirement to catch the events as they come in and store them if there was nothing in process. So we use a structure very similar to the structure we used for event generation, where the events come in, they're held, they have a duration provided by the activity block, and they have a status divided by the decision block. In addition, please start processing. There we go. We have the item itself that must be delayed. So the items come in, and when an item is present, we allow processing to happen on the delay event itself. I apologize for these. There we go. But the signal coming out of the delay event prevents the items from processing. In this way, we hold events until they can actually affect an item. And delays, by definition, always occur before processing starts. These are the kind of things like, I need a man to come load the furnace, but the man is not available and will not be available for some time. That could be represented by explicitly representing the man as a resource, or it could be represented as a random event that says, once out of every 10 operations, I have to wait for the operator to show up some period of time. That's our distinction between delays and no starts. The stop and restart signal we have, it comes in on the shutdown connector, and the option is set to stop and restart. We've used the standard mechanism that was represented inside the block. The stop and resume response, because we only have one option on the activity block, requires a little bit more structure. And the structure I've chosen to use for this is to create a local shift. So we start off by creating a base shift, the shift that the activity block will work on normally, and we write the base shift's value to the database so that it can be queried. The write block is set up so that it only writes when the shift value actually changes. This is done for efficiency reasons. We next combine the base shift and the stop and resume signals into a custom shift. So we read the base shift value that we just created above, and as with the write, we set up the read so that we only read when the value actually changes. That way we're not constantly reading when nothing will happen. We then bring our stop and resume signal in. We put it through a not block to invert it, because shifts are a positive value. They signal true when they are on shift, and our events are a negative value. They signal true or down when the event is occurring and we have failed. So we have to take the inverse of one to combine with the other. We put them into an AND, and we put that into a custom shift value. Now, because we're combining these signals in a custom shift, the typical shift block that we're using has a blank internal table. It is always on unless one of the external signals tells it that it's going to be down. The stop and resume structure then uses an activity that is tied to our custom shift block. Now again, this structure was necessary because the current activity block only allows us to choose one response at a time. Merging things onto shifts causes an explosion in the number of shifts in a typical model, and that has consequences that ranging from extended model initialization times to problems copying and merging things because there are so many shifts now in the block. The activity block is then chose to use the custom shift that we developed before, and now it will both go off shift and on shift, both based on its operating shift, its true shift, and the combined stop and resume signal. And we dictate that our response to shifts is the stop and resume response. The stop and release response uses the preempt connector as described before, but because preemption does not prevent new items from entering the block, we have to add some additional structure to prevent entry in this case. Option one is we merge the stop and release signal into the stop and restart signal and put it in on the shutdown connector. Option two is we merge the stop and release signal with the no start signal and put a gate in front of the activity. Either one of those will work. All we care about is that when the block is in a stop and release signal, that it is down for the entire period. Okay? When an item comes out, is preempted from the activity, we determine the appropriate event response. We have to determine which signal triggered the release so that we can look at and decide which response we want. We can examine the remaining process time to determine which phase the activity was in, or we can put in a separate structure we'll represent later, and we have to select our appropriate response based on those. We then reset the delay, the process time that we stored on the attribute that came out of the activity block, and use it as required. Sometimes the event response will be more than just putting it back into the start of our event. We may have to trigger it to go somewhere else, so our event response determination has to decide how to route the item and where to send it. As I said before, the stop and release is the most versatile because we can program any combination of responses, routing, and or time usage that we want. And in a lot of cases, it becomes the most useful and used version. To represent all of this now in one combined structure, we get a few added blocks. We break our process up into different phases. Here, typically, we have a startup phase, a processing phase, and a discharge phase. The reason we do this as before is because the responses to the different failures during the phases can be different. We have a calendar block simply to represent the logic we use to examine all of the failures in the system. The calendar block examines the failures that occurred that affected the whole plant. It looks in the database and queries to find out those that affected the wing or the room. And internally it has the structures to generate events that affect only this particular piece of equipment. All of those are handled and hidden inside of the calendar block, and we won't go into all of that detail. Because we have our no start options, and our processes are always limited to having one item in process at a time through all the various phases, we surround the entire phase structure with a gate block to limit the number of items that can be in process. The stop and the no start structure, having been negated now to be a positive start, is the gate block is put at the start of the chain, and the no movement adds another gate at the end. Both of those signals are being generated in the calendar block. The delay structure, as we showed it earlier, is encapsulated here in the stopwatch block just for simplicity. Come on back, there we go. The calendar block now sets up and generates our three event signals: the setup restart, the process restart, and the discharge restart. Because when we choose to restart the process, we can have different response generators or different signals that choose to restart when you're in setup versus those that choose to restart when you're in processing. We have to generate a separate signal for each phase. Similarly, we have the setup and process release mechanisms. Notice there is no release mechanism for the discharge phase, since the discharge phase is in and of itself the release mechanism. We have the logic again encapsulated to determine the response. And in the case where the response can send the item to different places, we have logic for determining where and routing to those destinations. The processes that I use typically fail on start, so I count my number of cycles using an information block ahead of the setup phase. This also eliminates the logic necessary to combine the TD signals from the three phases. If we use the TD signal, we would have to have an OR block that looked at the TD signal from the activity block for each phase and combined them into a relevant number of cycles connector. Because some of our repair times and some of our processes can only happen when the block is occupied, we look at the pound-signed output of the first gate to see how many items are currently in process and feed that into our calendar block. We use the activity status signal and parse it to determine the busy signal, which can be used both for our number of cycles operations or as a where connector input. Alternately, we could look at the logic for the L connector on the block, but we have to parse that then if we don't want to multiply our passage of time value. So for our cases where we only have one item in process at a time, we examine the busy signal. So many years ago, I was talking to a customer, and he wanted to know how much work building a simulation was going to require. And being the smart aleck that I am, I gave him a terse and oversimplified response. The first response was that for any simulation model, 80% of the work required is in data acquisition. This law is most true when we're talking about reliability analysis. The data required to generate the probabilistic distributions used to represent our events is enormous. Even when we're provided with distributions and don't have to acquire the data on our own, the number of distributions can be quite large. Looking at each process and deciding how it will respond to each event requires a lot of face time with the subject matter experts on that process. Adding an additional complexity, we have the business of how will our repair operations be affected by failures in other parts of the plant. Determining our TTR times, not necessarily our failure times. So we get a combinatorial explosion in the number of connections we have to represent, and it becomes a very difficult and time-consuming process to figure it all out, and really exercises the creativity of the typical modeler. The second of the laws is that 80% of the value of a simulation project is the understanding gained through that data acquisition. A good modeler who's done all of his data acquisition, understands all of the processes, and has a handle on all of the failure mechanisms, can typically feel, in just a gut feeling, how certain events are going to affect the overall productivity of the plant. That knowledge is an understanding of your particular process is sometimes, and in my experience frequently, more valuable than the actual simulation model you're building. But it was the exercise of building the simulation model that gave you that expertise. So with that in mind, I think that's about all I have to say. I've fumbled enough. My machine has messed us up enough. And I hope that you got something useful out of all of this. Anthony?
Thanks, everybody, for attending. And thank you, Joe, for taking the time to put this presentation together for us.